chapter 2 today. We've been talking about the atom and atomic structure in regard to the discovery of the atom. Last time you felt pretty confident about calculating protons, neutrons, and electrons in atoms, ions, and isotopes, and your do now shows that you clearly mastered that material. And the last piece of the puzzle today is going to be on calculating weighted average atomic mass. We'll talk about why elements have weighted average atomic masses, how to calculate it, and then we'll make it a little trickier and see if you can calculate the atomic mass of one of the isotopes. So that's our goal for today. You want to be able to calculate weighted average atomic mass. All right, so we had finished up ions in your notes, and we're right here, weighted average atomic mass. And there's not much in the way of notes today. It's just a matter of being able to do these types of problems. At first, you'll need your notes to do them, and then you'll pull back on your notes and you'll be able to do them without it. The first problem we're going to look at is all laid out. A couple things I want you to label off, and then we will be able to work through this, and I think you'll feel very comfortable with it before you walk out today. Weighted average atomic mass is a weighted average of all isotopes of an element. And when we talk about a weighted average, this is going to be very similar to the way in which your grades are calculated. For example, you don't just take a test and let's say you get a 90 and take a quiz and get 100 and do a lab and get a 95 and do your classwork and get 100 and say, okay, I'm going to add all of those up and divide by 4. That's an average, but it's not a weighted average. So if you did that, you'd have 290 plus 95, and you would divide by 4, and the average would be 96.25, or let's make it simple. That's if they were all weighted the same. But when we look at the different categories for your grades, they're not all weighted the same. And you don't have to copy this down, just watch. Your exams are 50% of your total grade. Your quizzes are 25% of your total grade. Your labs are 20, and your homework and classwork is 5% of your total grade. So when I figure out your total grade, it's a weighted average. Let's say that you take 3 exams and you get 100, a 90, and an 80. The average there is 90. Let's say you have quizzes and you have 100, a 100, a 90, and a 90. The average there is 95. Let's say on your labs you get an 80, a 90, and a 100. Your average there is a 90. And let's say all your homework and classwork grades are 100. You don't just add these up and divide by 4. To get a weighted average, you convert the percents to decimals or fractions. So you would just move the decimal 2 to the left, and you would multiply by this. So you'd have 0.50 times 90 plus 0.25 times 95 plus 0.20 times 90 plus 0.05 times 100. And the sum of those products would be your weighted average. And that's how we're going to go about it today. What you're going to see is you'll be given some percents, you'll be given masses, and you'll figure out the weighted average, similar to the way we determine your grades. keep that in mind as I show you this first example. Now this first example is laid out for you, which is nice because you don't have to copy anything down, but you may want to label a little bit, and then we'll write them out from scratch so you can see the whole derivation. In this first example, it says a sample of neon is 90% neon 20 with an atomic mass of 19.992 AMU. That's the first piece of information given. 10% is neon 22 with an atomic mass of 21.991 AMU. And we want to know the weighted average atomic mass. And one thing we mentioned the other day is that atomic masses on the periodic table are weighted averages because when you have elements, there are so many isotopes for that element that exist, and so you have to take them all into account, and the way you do that is by a weighted average. So we have two isotopes here, one in green, one in blue, and we want to know the weighted average atomic mass. This 90% is the percent abundance of neon 20. Neon 20 is listed here. The percent abundance is 90. The same way I indicated briefly that instead of 50%, you would use a fraction or a decimal, you'd use 0.50. You're going to do the same thing here. So you're going to convert the percent abundance that is here to a fractional or relative abundance that is here, and we'll label that off on the next problem so you're clear on the nomenclature. From 90 to 0.9, all I did was either divide by 100 or multiply. Let's do it differently. I would either divide by 100 or I'd move the decimal 2 to the left. I'm going to multiply this relative abundance by the atomic mass of this isotope. I'm going to do the same thing for the other isotope labeled in blue. The second isotope is neon 22. I've got 10% of it, or divide by 100 to get 0.100, and then I'm going to multiply by its atomic mass that's also given right here. And I add these two products together, I get the weighted average atomic mass. Now when looking at sig figs, this can get a little tricky. I'm going to make it easy for you. Couple ways you can do it. Look at how many decimal places you have in the atomic mass reported. 3 decimal places, 3 decimal places. Report your answer in 3 decimal places. That's fine. Or you can do least number of sig figs. You've got 4 sig figs here. You could have made it 20.19 AMU. I'll take either one. So whatever's easier for you. This one's written out. We're going to do this example right here from scratch. We're going to label off all the pieces so you can see exactly how it works. And I'll show you how much work you need to show me. In this problem here, it says a sample of iron is 90.23% iron 55 with an atomic mass of 55.458 AMU. 6.22% iron 56 with an atomic mass of 56.11 AMU, and 3.55% iron 57 with an atomic mass of 56.842 AMU. So that's your 3 isotopes, and we want to know the weighted average atomic mass. And I'm going to make it pretty straightforward for you with the work you need to show so that you know exactly what's expected of you. So that problem is in front of you in your notes or on the Chromebook, and we want to work this. So I've got 3 isotopes. I'm going to label it so you can follow it. The first is iron 55. The second is iron 56. Again, the mass number is the number after the dash, as we talked about the other day. And the third one is iron 57. Of the iron 55, I have 90.23%. Now that's the percent abundance. I want the relative or the fractional abundance. So I'm going to move the decimal 2 to the left. I have 90.23%, so I'd have 0.9023. That's the fractional or relative abundance. For iron 55, and I'll multiply that by its atomic mass of 55.458 AMU. So for iron 56, I've got a percent abundance of 6.22. What would its relative abundance be? Bryson? 0.062. You got it. Move the decimal 2 to the left. Perfect. And we're going to multiply that by its atomic mass. And then finally, we've got iron 57. It has a percent abundance of 3.55. What would its relative abundance be? Are you Luke? Go ahead.
0.0355.
You got it. And some of the kids were confused with that. Just back the decimal up 2 to the left and you're good to go. All the percents together should equal 100, right? Because if you consider your grades, all of these percents should equal 100 if you have categories. So the percent abundances of these isotopes should equal 100. Well, what should all of the relative abundances be equal to? 1 is correct. Perfect. So we're going to multiply this relative abundance by its atomic mass, which is 56.842 AMU. And now I just want to make sure you're clear here. To get the weighted average atomic mass, what you're going to do, and look up at the screen for a minute, is this times this, plus this times this, plus this times this. And let's see what we get. Yep. Of course, you can get it. Anybody needs a calculator, he's going to open up the drawer and please help yourself.
This drawer. Wrong drawer.
No, no, the plastic middle drawer. There you go. You can just leave it open, that way they'll find it. And again, I can see here that I have 2 decimal places, so that's what I'm looking to maintain. And I've got 55.55 AMU. And I want you to really do some analysis on your answer. Make sure your answer makes sense. And let's take a look at that analysis here. When we do this analysis, this is the weighted average atomic mass. This answer must be somewhere in between all of these, and it's going to be closest to the one that has the highest relative abundance because you have the most of that isotope. And this answer is consistent. It's within these, and it's closest to this because of the highest relative abundance. So again, change percent abundances to relative abundances by dividing by 100 or moving the decimal 2 to the left. Multiply each relative abundance by the atomic mass provided, and the sum of those products is equal to the weighted average atomic mass. Questions? Yes. In terms of the sig figs, you're typically going to look for the least number of decimal places of what's given for atomic mass. So 3, 2, 3. I'm going to go in 2 decimal places here to the 100th. Okay, let's see if you can set up the next problem in your notes, which is at the top of the screen. Let's see if you can do that. If you can, great. I'll show you a variation that's a little trickier. If not, we'll do another one to make sure you're golden. And the next problem is actually a little easier than the first one. How did we do? What did we get?
39.1.
0. That's why I got 2.
When you're doing it, and like you find like the whole, when you multiply the percent and the atomic mass, when you find all the numbers, you have to round it up to like 2 digits, and then round it up to it.
No, no. This is, see how you have 1, 2, 3 decimal places here, and you have 2 decimal places here? You want your answer in the least number of decimal places, so you want it in 2.
I'm saying like when you find the number in your calculator, you have like those like.
What was in your calculator? Tell me what it says on your calculator. Okay, show me.
So like, when you like this, you have to like round up to like 6
6.71.
No, no, you don't have to round at that point. Yeah, I see what he's asking. So his question is, when you get the product of these two, should you round and round? Nah, just make it easy. Throw it all in the calculator, get an answer out, and then round the answer. So in your notes, I showed you what the products were here, but you don't need to show me this or this. You can show me this, and the answer, and that's full credit. So what I've written here, like this, and that, full credit. I listed these two here because I think it's easier for you to follow, so I do recommend it. Okay, so we said the two relative abundances, or all the relative abundances, must equal 1, because all the percents have to equal 100. So these were very straightforward, where you got the pieces and you had to find the weighted average atomic mass. The way you can make this a little trickier is I could give you all the information on one of the isotopes. I could give you the weighted average atomic mass, and you could figure out the information on the other isotope. And that's what we're going to look at here. You'll be given this piece, you'll be given this. Can you find these? Let's take a look. We'll do this example together. We'll see how you feel. If you've got it, you'll do the problem. And then I have 5 practice problems in your classwork to hammer the point home, and you should be golden for your quiz on Monday. All right, in this problem, I'm going to write this way on my paper for this problem because I'm going to do it horizontally because it'll be easier for you to see. It says silicon has an atomic mass of 28.086 AMU. That is the weighted average atomic mass on the periodic table. So that's what we were finding previously. It's now given. 2 commonly occurring isotopes of this element exist in nature. One isotope, Si-27, has a percent abundance of 91.23 and an atomic mass of 27.110 AMU. We want to, let me put that in a different color, it'll be easier for you to see. There we go. We want to calculate the atomic mass of the other isotope. So let's lay this problem out. Ouch. All right. So the atomic mass, this is the weighted average atomic mass that everything is going to be equal to at the end, is 28.086 AMU. The first isotope is silicon 27. The percent abundance is 91.23, so the relative abundance is 0.9123, moving the decimal 2 to the left. And the atomic mass is 27.110 AMU. We need to find the relative abundance of the other isotope and then calculate its atomic mass. So that is my setup for the problem. So the first thing I need to figure out is the relative abundance of the other isotope. How can I do that? Exactly. And that's the easiest way to go. Some of you in your head may prefer to do 100 minus 91.23 to get 8.77 and then move the decimal point. Whatever rocks your world is fine. So you have 0.0877, and we got this by doing 1 minus that because all the relative abundances together must equal 1. Now we're going to solve here. Now this is just baby algebra that you are all very strong at. How would you go about solving for x? What would you do? Yep.
Divide 0.0877 from A to B.
You want to divide all of them?
No, it's from like the
Huh?
from the weighted number, the last number.
When you're doing your order of operations and you have to undo them, what do you typically start with? So for example, if you had 3x plus 1 equals 6, what would you do first? You would subtract 1 from both sides, correct? And then you would divide by 3. So the first thing we want to do is subtract this product from both sides. Does that make sense? Yeah. So our approach here is going to be 28.086 minus the product of this, and then we would after we subtract from both sides, how do we get x? Divided. So we're going to divide both sides by this. In your calculator, I will show you, and then you try it to make sure you've got it. So what I'm going to do is 28.086 minus this product equals, and then I'm going to divide by this. And I'm going to get 38.239 AMU. And I stayed to the 100th place because I had to the 100th place for both of those AMU. Now see if you got the same answer. Try and do it. Again, it's the weighted average atomic mass minus this product divided by that to isolate that factor or variable. Are you getting that answer in your calculator? Yes? On your quiz on Monday, I gave you one like this. So we're going to do another one, and there are 3 in your classwork. And if you work them all, I think you'll be golden for Monday for this concept. Do you want to try the next problem yourself, or you want to do it together? Okay. So on the screen now is the last problem. It's this one right here highlighted in yellow. set it up. I'll set mine up and we'll compare. How we doing? All right, I'm not going to show the answer yet. I'm just going to show my setup. So see if you have the same setup that I do. See if you got the relative abundance of this isotope. Did you set it up properly? Yes? Did you get this answer here? Some of you may have rounded slightly off. Make sure your answer makes sense. The weighted average atomic mass has to be in between these two, and it should be closer to the one with the higher relative abundance. Did you get it? Yeah? Okay. Couple things here. Weighted average atomic mass closes off this very short chapter, which is why I typically don't test on the chapter alone. This will be the first year I do because of the hurricane. Your quiz is very straightforward. It has one like this. It has some proton, neutron, electron type questions for atoms, ions, isotopes. I may have asked which subatomic particle is negative, just some very straightforward questions, so you'll read through your notes. For weighted average atomic mass, and you should be able to complete these 5 problems before you walk out the door today. In the classwork, which you already have, part 4 has 5 problems on weighted average atomic mass. That's what you want a high comfort level with before you leave today. Read through your notes. Be very comfortable with the classwork. Question. If I asked any people, I probably would have asked who discovered the electron, proton, and neutron. And if I asked anything else, it might have been which of the subatomic particles is not in the nucleus. Things you already were familiar with. It's pretty straightforward. Most of the quiz is on proton, neutron, electron calculation, but this is a 20-pointer right here. So before you walk out today, make sure you can do these with ease. And when you sit down and study, either Saturday or Sunday, do a few more. The nice thing in chemistry is you don't have to sit there and memorize tons and tons of notes and pathways, etc. You have to be able to do. And the more practice you do, the more successful you're going to be.
What do we round the final answer to?
In terms of this answer and the rounding, the atomic masses were reported to the 100th place, and that's what you're giving me at the end. Okay, and there's a little flexibility with that in some instances, but that'll be the easiest way for you to figure it out. Okay? Okay, so this closes off chapter 2, and hopefully you have a better understanding of atomic structure, how the atom was discovered, how the subatomic particles were discovered, who discovered them, their location, their calculation, and now the link to atomic mass and why on the periodic table atomic masses are actually weighted average atomic mass.